Is my screen visible to you all?
Yes.
Okay.
Yes, sir.
So today we'll be having a tutorial on RNNs and LSTMs, and we have divided this tutorial into three different components. Okay. So the first part will be showing you how to use RNNs on image data. Then in the next part we'll be we'll be showing you how do you configure LSTMs for NLP based problems. And then we have some supplementary materials where you can use the points from 1 and 2, and you can try your own things on both RNN LSTMs and even the encoder decoder based recurrent neural networks. So the supplementary materials, that part I'll be telling you at the end of the tutorial, like what all we have and what you can do. Firstly, preliminary, I'll be telling you about the RNNs and LSTMs first. So what I prefer is, like, I'll start with, I'll complete all three of them. I'll walk you through all the codes. Then we'll be sharing you the notebook. So I prefer that you. Okay. So I'll be sharing you the notebook at the end of after I complete all the three. You can try them, and in case you have any doubts, like, we'll be here till 7, so you can ask us. Or at a later point, if you still have doubts and you're still trying out things, you can contact us or post on the channel. So coming to RNNs, since we are working on image data, the major transmission libraries have to be imported, and other things that are necessary for training them are optimizers, the neural network modules, and the data loader part, which also to be imported. Then the device part on CUDA you are already familiar with, so I'm not covering that part. Next, coming to the point, we have the hyperparameters. Some of them are hyperparameters, some of them are the input specifications to the network themselves. So the input size, since the image data we'll be working on is MNIST, the input size is 28 cross 28. So here we'll be taking out something like, we have an image which is a square kind of a thing, 28 cross 28. So we'll be considering each row as one sequence which has 28 features. So uh, our each row will be one sequence. So we have 28 sequences, and our input size or feature size is 28. So that is the input size given over here. Then hidden size here is the uh, hidden feature size, that is the number of features on the hidden layer takes. And then we have the number of layers that actually indicates how many RNNs are you going to stack together. So RNN components. So here number of layer means 2. So it means that you stack 2 RNNs one after the other. Then the number of classes is 10, because the MNIST is a 10 class classification problem. So this number of classes we actually use while configuring our fully connected classification network at the end after the RNN is there. Then the sequence length part I already explained on the top. Then learning rate is a hyperparameter you choose, like, after few experimentations or intuitively. Then we have batch size, which is also chosen based on the memory requirement of your own system. And we have epochs. Here we have given 3 epochs just to show you things quickly, but you can try out more number of epochs also. So let me just run these things quickly. Uh, yes. So for time being, I'll be running the next ones also. Meanwhile, I'll explain you all these things. Next, coming to the recurrent neural network. So here there are a couple of things that you have to take into consideration when you are building it. One is the hidden layer size that you have to pass up, then the number of layers that you have to pass up. So just like any linear layer or convolution layer, we have in PyTorch the inbuilt RNN class, which helps you create an object of the RNN. So the input it's just give me a minute. The input it takes is something like the input size, which is the input feature size. Then the hidden size, like we already discussed, the hidden layer feature size, and the number of layers. Number of layers is here is nothing but the number of stacking plus number of RNN components you are going to have in between. Then there are two representations, something like batch first, which is true or false, which is a Boolean thing. So what this essentially is suppose we have a sequence which is of length t, and then we have in each sequence, I mean each component of the sequence which has features of say m cross n, and then we are taking a batch size of say 64. So we can write this tensor in two ways, right? 64 cross t cross m cross n, or we can write it as t cross 64 cross m cross n. So when we say batch first is true, it takes the tensor dimensions as 64 cross t cross m cross n. If you take it as, if you give it as false, it considers the first element of the tensor as sequence length, and then it considers the tensor dimension as t cross 64 cross m cross n. After this, there are a couple of more parameters which we have not used here. One of them is the uh, bidirectionality, which is also a Boolean thing. So if you give bidirectional, it will take both from left to right and right to left. And if you give bidirectional as fall, it will take only from left to right. So that is the default thing. And in case you want to specify any dropouts and bias also, that can also be specified. They are the additional parameters that this particular function takes in. And the last parameter that this particular function takes in is nonlinearity, which is by default tan h, but you have an option of specifying the nonlinear activation function as relu also. So in brief, like this is the RNN layer that you construct, and since we take the hidden size and number of layers as the parameters uh, to the input of this entire class, so we have to declare as self dot hidden size and self dot hidden so that we can use them again over here and in the subsequent parts of the forward function as well. So that completes one part of RNN declaration. Once we have the output from RNN, we have to do the classification task. So for which we would be needing a fully connected layer. So for that, the number of nodes of that will, I mean, the number of input nodes for our fully connected layer will be the hidden size or the hidden feature size into the sequence length, and our output will be the number of classes. So a single linear layer will do. And since we already have an activation function at the end of the RNN, which by default is tan h, we don't need to specify anything here. In case you want to use ReLU, you can specify it explicitly. So this completes definition of our fully connected layer as well. Now coming down to forward pass, that is whenever you call this function with a specific image as input or a uh, sequence of features as input, then what you have to do is something like just a second. Then what you have to do is because the first time you will be training, there will be no hidden state. You have to initialize that particular initial hidden state, that is h naught, which is given over here. So that will also follow the same convention as your input. So that is the number of layers. Then the size of x is nothing but what we say. Size of x is the batch size. So since we have already declared batch size over here, it is 64. You can hard code 64 here, but that will not work in all the cases because when your entire data set size is not an exact multiple of 64, this usually gives rise to a runtime error. So it is preferred that to dynamically pick it from whatever batch size it receives, you can compute the size and take the first element, which is the batch first, as say, and then the hidden size. And there, since there are two layers, we need like two h knots for each of them. Then we initialize h naught, we push it onto our device, whether it is GPU or CPU. After that, we pass both our initial hidden state and the input to RNNs, and we get the respective output. Once we get the respective output, since we have to pass it down to our fully connected layer, we have to like flatten it out. So the flattening operation is given out here, and then after that you have your classification output. So in case if you want to have probabilities at the top of this, you can add any other layer like softmax, or in case you are doing any multi-class classification, then you can add something else like sigmoid over there. So this completes the part of the construction of the network. Then loading onto data, since you have already been working on assignments and the other parts of the tutorial, the previous tutorial also on MNIST. So the data loader part is directly from PyTorch database. So you just give the root directory and download it. I think I have run this. Yes. And then here is the model initialization part. Since we have already declared all these variables on the top, you just use them, run it, and it is important to push your model onto the device, whatever you are using it. Then coming down to the loss is also like something very specific to the problem. Since here it is a binary, here it is a multi-class classification, you can use cross entropy loss, and optimizer is also of your choice. Since Atom is proven to be like performing really well on majority of them, so we have chosen Atom to show it to you over here, and you give the learning rate which is configured over top. Now coming down to the training part, uh, you just take the data, you just iterate over the data loader, push the data onto the device and your labels onto your device, compute and do a forward pass of the network, get the scores, compute the loss. Then here you will be doing like zero gradients, clearing out all the gradients that were there before. After that, in loss.backward, you will be computing all the backward gradients, and in optimizer.step, you will be updating all the weights. So these are two different things which are very important and not same. So in loss.backward, it is where you compute the gradients, and optimizer.step is where the weight update happens. So this completes the training procedure, and then you just have to plot the accuracies of. This is a small function that you can go through on your own self to check the accuracy of the trained model. Once we have the accuracy, and we just have to print them. So anybody has any doubts till now or anything else, you just feel free to ask. Then I'll move on to the LSTMs part.
Sir, what does accuracy mean here?
Okay. So here we are also doing the same classification task only. So here, instead of using a simple convolution or fully connected layer, we just write an LSTM version over here. So accuracy means like how, given the image data as a sequence features of row features, like how does a model do well on classifying the images? Is that okay?
If given if we have image data, sir, and if we remove if we give a text data like sequence of, then what
Yeah,
is
I'm coming to the text part. Okay, the text part is there in the next part. Okay,
okay, sir. Okay,
I'm
fine.
just anybody else, or can I move to the LSTM part?
So, while providing the input, so we are taking each row one by one, and we are providing many inputs, right?
Yeah,
Just like,
so yes, so
so
here
can
it
you?
is like yeah. So one image is 28 cross 28, right? So what we
Yes.
are doing is like I take a row which has 28 features. Like that, I have 28 rows. So my sequence length is 28, and my feature length is 28. Okay, so that makes my one image. Yes.
Okay. So, like, instead of that, could we also have done like, one to one kind of a thing, where like entire 72 pixels, I just send it, in the first thing only,
Okay,
and then
you just want to send like flatten the entire image out and send it as like
right. So, is
one
there any
sequence of seven and 748 images, 748 features.
780?
Yeah,
Yes.
784 features. Yeah, I
So
think
is
that can
there
be
any
done,
possible?
but your sequence length will be of like length one, right? What are you
Yeah.
going to do with a sequence of length one?
Yeah. So, my doubt was that whether it will perform worse or something like that than this.
I would leave it to you to try it out and let me know. Like I did not try it out, so you experiment it, like change the parameters over here and try it out and let me know. I mean, you
Okay.
just have to flatten the input instead of taking one by one row after the other,
Hmm.
and the sequence length will be one over there, and your batch size will remain 64. So you'll be passing out 64 images with 64 flattened images with a sequence of length of one.
Hmm. Okay.
Then, like, I mean, when you're passing out sequence length of one, probably you won't need an LSTM to capture the relationship between, because you won't have any other sequences to capture the relation between, right? So,
Fine. Yeah.
anything else, guys? Okay. Now, moving on to LSTMs for NLP part. let me just tell you LSTMs. LSTMs are also RNNs, but they have some additional gates to uh, to put it like in a very brief way to forget and remember the necessary information. Okay. So here also importing other things are the same as we do. We need the neural network library, we need the optimization thing, and we need the NN dot functional thing. So this is a small definition. Given a sequence and we have a dictionary, how are we going to extract the IDs for each of the sequence element? So where we are going to use it, I'm just going to come down. So here we took a very simple training data where you have a sentence and you have the parts of speech for that sentence. Okay. So the task here is to, like, given these things, I have to identify the respective parts of the speech. Next, coming down. So after that, what we'll be doing is, like, given in the training data, we'll be taking out all the sentences and tags. Then what I am going to do is, like, for each word in the sentence, I'm going to add it to a dictionary, and I'm going to take the length of the word as the what we say, a number, which is a unique index, suppose. Okay. Then for tags, like, since we have only 3 tags over here, I'm just going to assign random numbers. And then I'm going to declare 2 variables, which are my hidden dimension size and embedding dimension. Okay. So the output of this would be something. Just a minute. So here what we are doing is something like, since the computer only understands numbers, the sentences we are going to, each word in the sentence, we are going to map it down to a unique number, which is nothing but length of the word. And once we have that thing, then we are going to map it down to an index as well. So that part I'll be looking at later. I think that is somewhere over down, but let me cover the LSTM network first and then we'll go there. Construction of LSTM is also, like, very similar to RNN. Here, what you have to do is something like, the hidden dimension is embedding dimension we have already defined over here. Hidden dimension is also the same as before, the number of hidden features. Now, embedding dimension is your word embeddings. So this is something like word to vec. You can refer to what actually NN.embedding library to see how they're actually doing the embeddings over here. So NN.embedding is a thing very similar to word to vec, which gives you given a vocabulary thing and it gives you the embedding of that particular word. So once you have this word embeddings thing declared over here, then LSTMs is like, you give the LSTMs take the embeddings as input and it gives you the output, and it takes the input as the hidden dimensions also. So here also you have some more additional parameters like bidirectional and bidirectional also. This it stands the same here. So if you want your LSTM to capture the features in both the directions, that is from left to right and right to left, you can use bidirectional. Else you can use, you can declare it false. Even dropout is there. Then we have the batch first thing here also. So based on your own representation, like how you're declaring, you can use that, and number of layers. By default, the number of layers is 1. So here I did not declare any number of layers. So here it means like we are only using one NSTM block. So in case you declare more number of them, then you have multiple LSTM blocks. Then similar to RNN, here also we need to have we need to have a linear layer to do our classification part. So the output size of LSTM will be the input size of the linear layer, and then we have the target size, which will be our classification output. Number of classes in the output. Then once you have each sentence that is in the forward pass, you get the embeddings. Once you get the embeddings, you forward it to the LSTM, and after that you flatten it out and you forward it to your fully connected layer. And here we have log softmax, which will be the log of probabilities that will be giving you the scores. So yes, now as per the definition that we have declared over here, we will be putting up the embedding dimension, hidden dimension. Then there is the vocabulary size that you are going to do. So that is nothing but the size of your dictionary, because size of the dictionary you are creating over here, because here you are capturing the length of each word. I mean the word and the length of it as a key pair thing. So the length of the dictionary would be the vocabulary size, and your target size would be the, I mean the length of the part. I mean how many parts of speeches you have. So the length of this particular dictionary over here, and this will be the number of your output classes also. Then loss function is again a problem specific thing. So here we are using negative log likelihood loss. And since there we were using atom, we just wanted to use SGD over here, and the learning rate is also specified. Now coming down to the training process, first what you have to do is like you have to prepare the sequences. So it is something like this is something we have declared on the top, like prepare sequence. So what this particularly does is you have your training data, that is nothing but these two set of sentences, okay, and the corresponding labels. Wait a minute. Yeah, and you have your word to index, that is your dictionary. So what this particular thing does is like it constructs the sequence of say the dog ate the apple. So there are some random numbers like 3, 3, 3, 3, and 4. So it constructs the sequence as a number. So it does the same thing over here. So you can just look it up here. So it gets the IDs, it converts the IDs to it gets a list of IDs, and it converts the IDs to a tensor, and it returns it. So this is what you'll be passing to your network as an input. Now, once we pass it to the network, we get some tag scores, and we print the tag scores. So this is like a redundant part just to see how the model is actually performing on the scores, or what are the scores when we did not train the model. Something you just initialize the model and you want to see like how it performs without doing any training. Okay. Now, if I wait, did I run these all these things? I think I did not run it. Yeah. Where are we? Yeah. So for the training part, it's all over the same again. You read everything in the training data. You do the prepare sentence thing. Whatever sentences and tags you got, you just send it down into the model. You get the tag scores. You compute the loss, and it is. I think you are now well versed with loss.backward and optimizer.step. So you do those things, and the models keeps on training. Once you're done with it, when you're doing evaluation part, this is same as whatever we declared, we used over here. In the same way, you just see the, I mean, you put the model into eval, and then do with class.nograd such that the gradients are not computed. Then again, try to see the scores. So there, I mean, here there is a difference between the scores before and after the training process. So I think like we are a bit close in accuracy. Now coming down to supplementary materials, we have something interesting here. So this is up to your own interest, like how well you want to go around and play with things. But what we did, try and did an attempt over here. We provided with three different set of codes. So since you have already seen RNNs for image data, we have LSTMs for image data over here. So you can try uh, running this LSTM for image data code, which is like similar to an extension of LSTM, whatever you just saw, and compare the performance of pure RNNs and LSTM so that you understand how are LSTMs better and than RNNs, and probably then you will be more intuitive and diving into why they are performing better. That is one part of thing we have over here. Then next what we have is like LSTMs for text classification. So this is something that will run on a large corpus of data. So anybody who's really interested in text classification, you can just refer to this part of the supplementary material. And because it is LSTMs, the way you use an LSTM is same as we have told above. So we have provided the entire code over here. You can just read through it. If you did not understand any part, like you can come back to us and like we'll clarify it for you. And then we have something else interesting at the end. Yes. We have the encoder decoder RNNs as well, and this is also a NLP based task. So this is a bit more which has like all the pre-processing you do in NLP task, all those codes are also included here. So you can just refer to all these things, like how to get a general idea on how to do things if you're really interested and you have the time. Uh, and in case you have any doubts, like be sure to get back to us. But there are two, let me just tell you, there are two important things for the supplementary part 2 and part 3. So these have some additional data that you need to download and set the folder structure properly so that you can run the code. So the files were very large, so we did not include as part of the tutorial. So but they will run on CPU devices that is tested. So you can just try it out. So in case anybody has any questions, like let me know now. Otherwise, like if you want to try, we'll just upload the notebook and we'll give you another 15-20 minutes to try it out and come back with any other doubts. The notebook will be uploaded in chat and also the file section in the class materials part.